So today we are going to talk about inverses, which you learned a little bit about in Math 3. So by definition of inverses, if f of x and g of x are inverse functions, then f composed with g of x is going to equal x, and g composed with f of x is also going to equal x. So that's kind of just saying like one function is going to undo the other one, and we're going to talk about that tomorrow. But for today, we're going to talk about these second two pieces down here. So the domain of f of x must equal the range of g of x and vice versa. So basically, a function and its inverse, the domain and range are going to switch for those. And then f of x and g of x, the two inverse functions, will reflect over the line y equals x when graphed. So we're going to talk a little bit more about what all of that means, but that would just be like the definition that we're going to go with here. So for how to find inverses, the first step is just going to be to switch x and y. And so that's why the domain and the range are going to end up switching, is because your domain deals with all of your x's and your range deals with all of your y's. So after you switch x and y, then you just solve for y again. So here's an example, and the first thing I'm going to do is switch my x right here and my y. So I would have x equals 2y plus 7. And then now I just need to solve for this y again. So to go about doing that, I'm going to subtract 7 from both sides and have x minus 7 equals 2y, and then I'm going to divide by 2. And I'm going to end up with y equals 1/2 x, or x over 2, however you want to look at it, minus 7 over 2, or 3.5. Either way you write that is fine. But this would be the inverse of y equals 2x plus 7. So now I just want to kind of show you guys what I mean whenever I say that it's going to be reflected over the line y equals x. So the first thing that I'm going to do is just graph the line y equals x, and I'm going to leave that in there for all of them, just so that you guys can see the way that it's going to look. So I just want like a dotted line there. And then I'm going to graph my original functions. My original function was y equals 2x plus 7. And so I'm going to zoom out a little bit so you can see a little bit better that function there. And then my inverse that we found was y equals 1/2 x, and then it was minus 7 over 2, or 3.5. So you can kind of see on the graph, and whenever it's just lines, it's a little bit harder to tell. But you have this line y equals x right here, and then your two inverses, for one, they're going to hit that line in the same point at -7 in this case. But then they're also just kind of like reflected over that line. So like this is my original function. You have the point 0.7. And so then in my inverse, you should have the point 0.70 because those x's and y's just switched places in those. So this is kind of what it's going to look like whenever you're reflecting over that line y equals x. So now we're going to go a little bit more into why it's important to know that it's just flipping over that line y equals x. So first of all, not all functions have inverses that are functions. And so we're going to look at that a little bit for one. Because if the inverse is not a function, then you're going to need to restrict the domain so that it is. So then, to have an inverse that is a function must be, sorry, I didn't mean to be crossing that out. I thought I was going to be highlighting. But a function must be 1-to-1. Now I'm highlighting, okay. And that means for every x, there's only one y, and for every y, there is only one x. And so then it says it must pass the horizontal line test. So to find out if something is a function or not, you guys have probably seen the vertical line test before, but to find out if the inverse is also a function, that's when it's going to need to pass the horizontal line test. So let me go graph y equals x squared, and then we'll go from there. So I'm going to come back over to Desmos, and I'm going to get rid of what we had in there. And then now we want y equals x squared. So this is what that looks like, is this parabola here. So then Desmos does this cool thing where if you want it to do an inverse, then you can literally just switch x and y in the equation. So I'm going to do x equals y squared. So now you can look at it, and obviously they're reflected over the x-axis, but this bottom part down here, it doesn't pass the vertical line test, so that means it's not a function. And what that means is if you can imagine a vertical line just going all the way across the graph, like vertically, and if it can hit 2 points at once in any spot, so like I'm just going to graph a random line so you can see what I mean. So like this line, it's a vertical line, and it could be at any spot on the graph. But if it can hit 2 points on that graph, that means that this function that's being graphed, x equals y squared, that's not going to actually be a function. Because for it to be a function, anytime you plug in an x, you should only get one y. But like you can see right here, if you plugged in 5, for example, there are 2 possible y values. So that means this inverse is not going to be a function. So that's where it's going to get a little bit tricky and where we're going to have to restrict the domain, which is something that we're going to talk about. But basically, to figure out if any function has an inverse that's also a function, you can do the horizontal line test. So like, I'm just going to put a random horizontal line, and this is the same thing I used the other way for my inverse. But if you go up and down the graph with a horizontal line, then any place that it can hit 2 points, that's going to mean that the inverse is not a function. So if it doesn't pass that horizontal line test, then the inverse is not a function, and that means it's also not a one-to-one function, because for every y, there is not only one x, or for every x, there's not only one y. Either way. So that's what we're going to talk about in this next slide here. So to find domain restrictions, it says you're going to have to find the range of the original. So for the first one here, it goes ahead and gives us your domain restriction. So what we're going to do is we're just going to go ahead and try to find that inverse and then see if it works on the graph. So right now we have y equals x squared, so now we just need to go ahead and switch my x and y. So this is what we did a second ago on the graph. So it would be x equals y squared. And then I need to solve for y. So to get rid of my squared, I'm going to take the square root. And then remember, anytime that you take the square root, you're going to do the positive and negative version. So that's a plus or minus, if you can see it. And so then we're going to have y equals positive or negative square root of x. So we're going to go back over to the graph. And we already have y equals x squared graphed, but we need to include a domain restriction now because it told us that x was greater than 0. So now you can see it's only graphing half of that. So then our inverse was plus or minus the square root of x. So we're going to come over here, and I'm just going to do it as 2 separate ones. So I'm going to do negative square root of x, and I'm going to do positive square root of x. And so now that's going to graph it twice. And then you can kind of play around with it. Like if I don't want to look at one of these, then I'll just hit the button to get it to go away. So you can kind of tell now the one that we have shown is going to be our inverse because it's reflected over that line y equals x. But if I wanted to look at the other one, then I'll just turn that off. And you can tell this isn't a reflection. It looks like it could be like some sort of rotation or something. But either way, it's definitely not a reflection over the line y equals x. So that's not going to be part of our inverse. It's just going to be the positive side of the square root of x. So when I come back over here, I had positive or negative, but now because I graphed it, you know you only need the positive version. So then if you only need the positive version, you don't really have to write the actual positive, but it would be positive square root of x. All right, so now we're going to do the second one over here where you have y equals the square root of x plus 3. So first I'm going to switch my x and y. So I would have x equals the square root of y plus 3. And then I need to solve for y. So first I'm going to need to get rid of the square root. So to do that, I'm going to square everything. So I would have x squared equals y plus 3. And then the last thing I need to do is subtract 3. So now I'm going to have y equals x squared minus 3. So then is when I need to look at the graph. So I already graphed it over here for you guys. So you can see right here, you get half of a parabola looking thing. And then for the inverse, we got y equals x squared minus 3. So whenever you graph that, you get the whole parabola. So that's where we're going to have to start finding some domain restrictions. So, and I believe I put on here, if it'll let me look, to find domain restrictions, you find the range of the original, and then that's going to give you the domain of the inverse. So if you guys remember range from Math 3, that was just talking about all of the possible y values. So it's going to be the lowest point to the highest point on the graph. So from lowest to highest points. So then I'm going to come back over and I'm going to look at my graph. And I'm going to look at that original function. So I'm just going to turn off the inverse for right now because I don't want to see it. So I'm just looking at this original function, and I'm looking at the lowest point right here, which is at negative 3, 0, and it goes off to the highest point. So you can kind of tell this, it's going to keep going up forever, so the highest point is going to be infinity. So that range that you're looking at right there is going to be where y is greater than 0, because you're looking at that y value right there. So then whenever you're using that as the domain of the inverse, that means you're going to need for x to be greater than 0. And then I'm going to turn this back on. And now that I added that domain restriction in there, you can tell this is now reflected over that line y equals x, and it looks like the inverse and everything looks good now. So I'm going to come back over here, and so we need to add a domain restriction, and so it would be for all x is greater than 0. And then it can actually be greater than or equal to, because it's okay if it's 0 too. Because you saw on the graph over here, there's an actual point where y equals 0, so it's okay for there to be an actual point where x equals 0, which in this case, it's telling you it's undefined on the graph. That's just because I put a greater than sign instead of greater than or equal to. So let me change that to greater than or equal to 0. And then I can click on that point right there at 0, negative 3. So that should clear that issue up. Okay, so we're going to try another example here, and this time there's a negative sign in front of the square root. So we're going to see how that changes things. So first, we're still going to have switch x and y. So we would have x equals negative square root of y minus 5. And then we're going to need to get rid of that negative sign. So you can divide both sides by negative 1. And I would have negative x equals the square root of y minus 5. And so then this is going to look a little weird, but now we're going to square everything. And I know that negative x squared looks weird, but just leave it like that. So negative x squared equals y minus 5. And then you're just going to add 5 to both sides. So you would have y equals negative x squared and then plus 5. So we're going to go graph that on my graph over here. So negative x squared plus 5. And then plus 5. Okay, so now we have, this is our inverse up here, and then this is our original down here. And so we know that we're going to need to restrict the domain so that this looks more like a reflection, because we have a whole parabola up here and only just like the half that comes from the square root down here. So what we're going to do is we're going to look at the range of this original function. So it starts, well, it doesn't start. The lowest point is negative infinity, so it goes from negative infinity to the highest point. So it ends right here at 5, 0. So the highest point is going to be 0. So that means that the range of this is going to be y is less than or equal to 0. So since I'm switching the range from the original to be the domain of the inverse, I need x to be less than or equal to 0 for my inverse. And so it would be typed like that. So then now this looks more like a reflection. We only have half of that parabola, which is what we have down here, and that is what we needed. So that means that whenever we are restricting the domain in this one, we need for x to be less than or equal to 0 instead of greater than or equal to 0. So that is for x less than or equal to 0. And then, okay, so there is one more here. And in this one, it is giving us the domain already. So that means we just need to go ahead and find the inverse and then see if it works. So I'm going to switch x and y. So I would have x equals y plus 1 squared plus 2. And then I need to start solving for this y. So I'm going to subtract 2 from both sides. And I have x minus 2 equals y plus 1 squared. Now I need to take the square root. So I would have the square root of x minus 2 equals y plus 1. So I don't need that parentheses. Y plus 1. And I'm going to wait on the plus or minus for the square root, and I'm going to use the graph to determine which one it needs. So now I'm just going to subtract 1 from both sides. So I would have y equals the square root of x minus 2, and then minus 1. So I'm going to go graph those. Okay, so I went ahead and typed in my graphs here. So I put the domain restriction that it gave us, which was x is greater than or equal to -1. And then I just typed it in with the positive version of that square root sign, and you can tell that these are a perfect reflection over the line y equals x for us. You can click on some points if you need to feel more comfortable. You can see that we have 3, 0 on the inverse and 0, 3 on the original. So they just switch x and y, which is exactly what we want them to do. So we're going to keep that, this y equals the square root of x minus 2 minus 1 as our inverse. So we don't have to worry about doing anything with the positive or negatives because we already had the domain restriction in the original. So then I made one more note over here. So if a quadratic function has the domain restricted where you have x is less than a number, so like right here we had greater than or equal to -1. If it says that it's less than or equal to a value that's in the vertex, because typically that's where it's going to be, is wherever the vertex is, then the inverse, which is going to be a square root function, it'll be negative. So I want to show you what I mean by that. So say if our original, instead of being greater than or equal to -1, let's say it told us that it was less than or equal to -1. Then whenever we did this step right here where we took the square root and I told you guys we would wait and see about what sign to put out front, basically if it had been less than, then when we graphed it, you would be able to tell it's not an exact reflection So you can go back and just add a negative in front of your square root. And that should take care of it, and it'll give you the inverse where it's like the perfect reflection like we had earlier. And you can tell, it won't click on that point for me for some reason, but you can tell that in the original, you have that point where the vertex is at -1, 2, and then in the inverse, you have it at 2, -1. And then they go off in the correct directions to be a reflection over that line y = x. So that's how you would take care of that anytime that you have a less than sign there instead of a greater than sign. So if you have any questions about any of this, just let me know. The biggest thing that is building on last year is including those domain restrictions. So please just use Desmos and it should help you out a ton on finding those inverses correctly. So I hope that helps, and just let me know if you have any questions.